Okay, now this is called the electrochemical series. If you see over here, this is called the electrochemical series. So this is what you guys memorize in high school, but this is actually called the standard reduction potential table. Okay, standard reduction potential table. So let me explain each of these words here. Let me explain reduction. If you look at every single equation here, right, you look at every single equation here, you will notice one thing. All of the equations are written in a reduction fashion. You see, every single equation is written in reduction fashion. That means electrons are written on the left hand side of the arrow. So all of these equations are written as reduction. Got it? Okay, so that's why it's called the reduction. The next word that you see here is standard. Now, what does standard means? Standard means that this table that you're seeing here was created under standard conditions, which is 25 degrees Celsius or 298 Kelvin. That's number one. And then anything which you see here is aqueous. Anything that you see aqueous, right? Anything which is aqueous here, anything which is aqueous, or everything here is 1 molar. Okay, so every aqueous solution that you are dealing with in this table is 1 molar. Everything is 1 molar. Okay, that's what it means. So second thing is all solutions are 1 molar. And the third thing is, when you're dealing with gases, let's say gases here, there is gas here, let's say there's gas here, wherever else you see gas, right, wherever you see gas, the gas is at 1 atm or 100 kilopascal. So that is why the word standard comes in. So this data that you're obtaining is done at 25 degrees Celsius, at 1 atmospheric pressure, and at concentrations of aqueous solutions at 1 molar. That's what it means. Okay, and then the word potential is actually an English word, right? It means ability. So this at the end here, this is called E naught. Okay, E naught is called an E naught. That's how we pronounce this. So it's actually written like this: E, and then there's a line that goes like this. Is E naught. Okay, so it's called E naught. It's the voltage. So this is the potential. So this is the potential to pick electrons up. This is the potential to pick electrons up. The way I look at it is, I like to look at it as love. The love to pick electrons up. Okay, the love to pick electrons up. Let me clear the page. Okay, so it's the love to pick electrons up. You see, basically, let's say we have 2 elements here. Let's say we have 3 elements. We have this guy, we have this guy, and we have this guy. Okay, so all 3 of them say we love electrons. We love to pick electrons up. Okay, we love to pick electrons up. And fluorine says I love to pick electrons up. Aurum 1 says I love to pick electrons up. Chlorine says I love to pick electrons up. But there is a measure. If you look at this number here, you know who loves to pick electrons up more. Obviously, you can see fluorine is the one that loves the most to pick electrons up, and he actually has data to tell you, I love to pick electrons up 2.87. You guys 1.68, 1.36, you don't love electrons as much as I do. So electrons fall in love with fluorine more. So fluorine is known to be the most electronegative, right? Electronegative element. Okay, it has the highest electron affinity in the entire Earth, or maybe other universe, we're not sure, but on Earth, yes. So what you will notice here is, as we go down here, the love becomes less. Okay, like for example, this Tandem 4 here loves to pick electrons up, but okay, not so bad, I love it, but if I don't have it, it's okay. Then here you will notice hydrogen is 0. Okay, hydrogen is 0 because hydrogen is the standard. It's the standard. So scientists around the world have decided that hydrogen will be given the value of 0. When we compare hydrogen with anything else, that's how the value will be obtained. Okay, for example, let's say what we prepare a half cell, right? Let's say we prepare a half cell. So one half cell would be, let's say, copper, let's say. The other half cell will be, let's say, hydrogen gas. Okay, hydrogen gas being pumped into a solution of hydrogen ions. Of course, since it's a gas, we cannot just open it like that. There is usually a container that goes something like this. All right. And then there is copper, and then just connect this. So what happens is when we see a voltage, okay, so there's a salt bridge, right? When we see a voltage, the voltage will show 0.34. Okay, it will show 0.34, like what you see here. Where is copper? You see this here. We assume hydrogen is 0. That means it is taken as 0.00. So who did this? Scientists. Scientists just say, let's assume hydrogen is 0, and then we compare everything else with hydrogen. So all of this data that you're seeing here, right? All of this data was actually obtained by comparing each one of these elements with hydrogen. So this is called the SHE electrode, okay, standard hydrogen electrode. Where is it? Okay, so later on you can read this. Is not so important, but you can read this. Is here standard. You can see this. This is the standard hydrogen electrode. So hydrogen is pumped in at 100 kilopascals. Solution is 1 molar, and we use a platinum electrode because hydrogen does not have an electrode. Okay, hydrogen does not have an electrode, so we use a platinum electrode. So what will happen is, you see in all of these cases here, the value for zinc is obtained by comparing it with hydrogen. Okay, so SHE here, standard hydrogen electrode. So every single value, like in the case of copper, is also compared with this. Okay, so in this case, you see electrons are flowing from zinc to hydrogen, 0.76. Here is from hydrogen to copper, 0.34. All right, so when it's flowing from hydrogen to copper, so basically what is happening is hydrogen is becoming hydrogen ions plus 2 electrons. So the electrons are going up here, here, and coming here. But in this case, what is happening is electrons are coming up from here, here, going here. So here hydrogen ions are picking up electrons and becoming hydrogen. That's what is happening here. Okay, you don't have to worry about this. This is not important, but this is how those data, the data that you're seeing, is obtained. Okay, so then finally you get a table like this. So every single thing that you see on the table, the electrochemical series, is obtained from hydrogen half cell. Okay, not important to you, but that's all I want you to know. Now back to this again. Let's clear up the page again. So right at the top here, right at the top corner here, this is our strongest oxidant. Okay, that means this guy absolutely loves to pick electrons up. Right at the bottom here, look at this guy here. This is lithium ion. This is the weakest oxidant. Okay, weakest oxidant, absolutely hates to pick electrons up. But I want you to notice one thing. These arrows are reversible. They are reversible. So what does it mean? What does that mean? It means that if we look at the same equation in reverse, let's say lithium goes this way, positive 3.02 volts. That means lithium metal absolutely loves to lose electron. The ion, his partner, the ion hates to pick electrons up, but the metal loves to lose electrons. So same thing with potassium, right? Potassium, because we know metals love to lose electrons, yes or no? So this is going to be 293. But if we compare lithium and potassium, we realize lithium is a better reductant because it absolutely loves to lose electrons more than potassium. Okay, slightly more, about 0.9 more, but that's what it is. So if we look at this table here, right? Okay, what I want you to notice is this. Right at the bottom here, this guy is the strongest reductant. Okay, so this is the weakest oxidant. Oxidant means somebody who loves to pick electrons up. So at the top here, strongest oxidant, this would be the weakest reductant. Okay, weakest reductant, because it makes sense, you know. If I love to lose electrons, my partner, weakest reductant, okay, reductant. If I love to lose electrons, why would my partner want to if I love to pick electrons up, why would my partner want to lose electrons, right? So because you see, in this case, if I do it like this, 2Fe minus becoming Fe, 2 plus 2 electrons, this value is negative 2.87 volts. This means that fluoride absolutely hates to lose electron. All right, so the moral of the story is, if I am a strong oxidant, my partner, so my partner is this guy here, okay, is a weak reductant. But if I'm a strong reductant, then my partner is a weak oxidant. It's opposite. I cannot be both. I cannot be strong and weak. Does this make sense? I have to be strong at something and then weak at something else. That's how it works. So that's the electrochemical series. And this series is very important because it will be given to you during the exam, and you're going to be using this table to predict reactions. And that is what we're going to do next. Okay?